Hello everyone, welcome back to our course on abstract algebra. Today we're going to talk about something called internal direct products. So remember that our goal is to classify groups, in particular finite groups if possible. And what we did last time is to create groups from old groups as direct products, what we call external direct products. So for example, we created things like um, a new group by doing the direct product of S3 and Z modulo 2Z. This is a new group, and it is a new example of a non-abelian group because S3 is non-abelian, but now it's a group of order 12 that is non-abelian, so it gives us new groups. So the goal today is to realize, to try to understand when a group is actually a direct product. This has two applications. One, we are trying to classify groups. So when we see a group and we realize it is a direct product of two groups we already knew, then this is not an essentially new group. It's a group sort of we already knew how to build. And second, when we have a group that is complicated, a new group comes up that is a complicated group to study, by realizing it, if it is possible to realize as a direct product, then we understand a lot more about this group because we understand S3, we understand Z modulo 2, and we understand how a direct product works. So we want to try to realize when, so the goal now is to understand if a group G is isomorphic to a direct product of to its own subgroups. Okay, so we're going to try to see is if we can build it out of the direct product of two of its own subgroups, where H and K are actually subgroups of G. If so, then we say that G is the internal direct product of the two. Let me give you an example before I try to define this formally. Let me give you two more examples. So, for example, remember U8, which is, if you want in another notation, Z modulo 8 cross. So the units modulo 8, and those are 1, 3, 5, and 7. Modulo 8, we have proved before that U8, so before we proved that U8 is actually isomorphic to Z modulo 2 cross Z modulo 2 as abstract groups. And that isomorphism was actually not very satisfying. We just did a bijection. 1 goes to 0, 0, 3 goes to 1, 0, and so on. But we realized that this U8 is isomorphic to a direct product. So what I want to try to realize U8 as a direct product of two subgroups. So now I'm going to let H be the subgroup 1, 3. I know this is a subgroup because it's the subgroup generated by 3. And let K be the subgroup generated by 5. These are subgroups. And now I'm going to actually suggest there is an isomorphism from H cross K to U8 given by a pair HK goes to H times K. Okay, so a pair of elements modulo 8 goes to HK, H times K mod 8. So these are both pairs modulo 8, and this is a class modulo 8. And it turns out this is a bijection. Let's see what happens. So 1, 1 will go to 1 times 1, so it's 1. 3, 1 goes to 3. 5, sorry. Let's see. Now we have another pair in here would be 1 comma 5 is in here, and that goes to 5. And the pair 3, 5 goes to 3 times 5, which is 15, and 15 is 7 modulo 8. So we do get a bijection. Great. Now, does this respect the group structure? Is it really an isomorphism? So let me prove that phi respects group structure. So let's see, how much is phi of a pair hk times another pair h prime k prime? That will be phi of, I know how multiplication works in a direct product, in the direct product of h and k, that will be component wise, h prime, k prime, and I know how phi was defined was the product of the h times the k, so this is h prime, k prime. This is actually a number modulo 8, but now the numbers, the multiplication in the units modulo 8 is abelian, so this is hk h prime k prime modulo 8, and here I'm using that u8 is abelian. And this is, by definition, phi of the pair hk times phi of the pair h prime k prime. And therefore, it is preserving group structure. This is for any h and h prime in h, any k and k prime in k, and therefore it works for all pairs, and thus phi is an isomorphism, and the direct product of h and k is isomorphic to u8. And since these are subgroups of U8 itself, we say that this is an internal direct product. There's one more condition that we're going to add on for it to be an internal direct product. Actually, we also want that the product of the elements of H times something in K is actually equal to U8, and that their intersection is trivial. So it turns out that those two things are also true in here. We'll talk more about those in a second. Now, going back to the fact that U8 is isomorphic to Z modulo 2 cross Z modulo 2 that we had seen, just sort of like without much of an explanation of why these were isomorphic, let me go back and now see that U8 is isomorphic to H cross K, but each one of those, this is precisely the subgroup generated by 3 direct product, the subgroup generated by 5, right? And those subgroups themselves are isomorphic to Z modulo 2. So now I can actually define an isomorphism between U8 and Z modulo 2 cross Z modulo 2 that goes through this internal direct product that we have described. How so? I can take A, B, the pair AB can go to, well, the element in the direct product 3 to the A and 5 to the B, and then this isomorphism here, which was phi, what it does is sends these to their product. So this actually gives me an isomorphism to from Z modulo 2 cross Z modulo 2 to U8 that sends the pairs AB to 3 to the A times 5 to the B, and it turns out this is an isomorphism of groups. So now I get an isomorphism that is not just written out as a bijection, one goes to such and such. It is actually a bijection that makes sense, and you can easily prove that this is an isomorphism, that it respects, that it gives you a bijection, and it respects group structure. So show that. Maybe it's a good exercise to show that psi of AB plus A prime B prime is the same as psi of AB times psi of A prime B prime. Okay, so exercise show that. Great. So now let me show you another example. It turns out we're going to prove, so maybe this can be an exercise, prove that D6 is isomorphic to that other group I talked about at the beginning. So in fact, this direct product of S3 cross Z modulo 2 is isomorphic to a group we already knew. It's D6. And D6 is a group that is non-abelian of order 12, but it turns out is exactly this. What we're going to prove is that D6 is actually an internal direct product of an H times a K, where H is the identity and R cubed. Remember that, recall that D6, where that D6 is generated by two elements, R and S, a rotation that has order n, a reflection that has order 2, and such that SRS is R inverse. Okay, so it turns out that 1 and R cube in this case, because, well, that's, and here is a 6 in this case, 1 and R cube is a subgroup of order 2, and K given by the identity R squared, R to the fourth, S, R squared S, and R to the 4S is another subgroup of order 6 in this case, which is actually isomorphic to S3. So we're going to come back to this later and show that this is in fact true, that D6 is the internal direct product of the two. So how do we identify if a group G is the internal direct product of two subgroups? So let's write a proposition. Let G be a group and let H and K be subgroups such that one, G is H times K. That H times K is the set H times K for any H in H and any K in K, exactly in that order. Okay, it has to be exactly in that order. That is an element of H times an element of K, and that set has to give you back all of G. 2, that H intersect K is identity, and 3, that K and H commute for any H in H and for any K in K. Then G is isomorphic to H cross K via the isomorphism given by H cross K goes to G and sends pairs HK to H times K. If so, we say that that G is internal direct product of H and K. Okay, so this is the definition of internal direct product, is if this happens. Okay, so let's prove this proposition. So here is the proof of our proposition. We have a map that goes from H cross K to G. HK is sent to HK, and we want to prove that this is an isomorphism. So first, let's prove that this is, well, it is well defined, because if H is in H and K is in K, these two are subgroups of G, so they are elements in G, and therefore H, what would be really H star K, is in G because star is closed on G. Okay, we have the closure. We have the G is closed under a star. Second, I want to prove that phi is a bijection. So let's prove that is injective, first of all. So suppose that phi of hk gives me the same as phi of h prime k prime. That would say that h times k is the same as h prime k prime. And now I would like to conclude that this pair and that pair are exactly the same. One way to do that, a very common trick in mathematics, is when you see an equality like this, is to put things that are apples with apples and pears with pears. The apples in here are the h's, which are both in a subgroup h, and the k's, which are both in a subgroup k. So what I'm going to do is multiply on the left by h prime inverse, and on the right by k, so that I have this expression. Now, this part is in H, and this is in K because H and K are subgroups, therefore they are closed under star, under the multiplication in the group. Therefore, this element is in the intersection. But the intersection, by assumption, remember our assumptions in the theorem, the intersection is trivial. So the only thing that is in the intersection is E, and therefore both sides of the equation are E. And then if you unravel what those mean, for example, h prime inverse times h is E, if I multiply again on the left by h prime, now I get that h is h prime and k is k prime. And therefore, the pairs are the same. Hk is the same as h prime k prime, and therefore phi is injective. Great. Is it surjective? Well, yes, because by assumption, we have that hk is G. So if G is in G, there are some H in H and some K in K, such that G is HK. And what that means then is that phi of that pair in particular will be HK is G, and therefore I have surjectivity. Okay, so these two things they tell me that phi is bijection. And now I need to know that phi respects group structure. So let's see if that is true. Well, phi of hk times phi of h prime k prime is how much? Well, let's start. Well, sure, I can start on this side and then see if I get to phi of the product of the pairs. So phi of hk and phi of h prime k prime is hk h prime k prime. Okay, that is the product of the phi's. Now, by assumption, and this is important, the h and the k's commute. So we have that hk equals kh for all h and k's in k, and therefore I can make the k and the h prime commute. That is h prime and then k prime. But this is now h prime is an element of h, so this is the same as if I send over the element h prime k prime by via phi. And then this is the same because of the way multiplication works in a direct product. This is the pair hk times the pair h prime k prime. And now I just want to point out that this is the product in G. These are all products in G, but when I'm here, that is the product in it is the star of the direct product H times K. Great. So, but this is for any H prime, K prime, in H in K, and therefore it respects the structure. So phi is an isomorphism, and H cross K is isomorphic to G, which is what I wanted to prove. So now we have a criterion to know when when a group is an internal direct product of two subgroups. So let's use it in the example we have already seen, that we have U8, I have H, a subgroup, 1, 3, I have a subgroup K, 1, 5, and I want to prove that U8 is internal direct product of H and K, of K and H, let's say. So what I need to check is the hypothesis of my proposition. First of all, HK is G. Well, let's see how much is 1, 3 times 1, 5. I do get everything that I want. I get 1 times 1 is 1, 3 times 1 is 3, 1 times 5 is 5, and 3 times 5 is 7, which is G. Great. Second, you can see clearly the intersection of H and K is just 1, which is identity in U8. And last, what do we need to check last? We need to check that everything commutes. So if I have H in H and K in K, I need to know that HK is the same as KH. But this is true because U8 itself is abelian. Okay, so that tells me that that all the conditions are satisfied, and therefore U8 is isomorphic to H cross K, and it does give me the isomorphism. The isomorphism is that any HK goes to H times K, which is the isomorphism that I had proved earlier in this particular example, that it is an isomorphism. So it is the internal direct product. Great. Let's see the example of D6. So here we're going to prove that D6 is the internal direct product of H is identity. Let me just write it as 1 and R cubed, and K is 1 R square R to the 4 S R square S R to the 4 S. Great. And so let's prove that. First of all, how much is HK? You can see that I can just get with 1 times anything in K, I get everything in K. So I get 1 R square R to the 4 S, R square S, and R to the 4 S. And then R cubed times one of those elements, I get R cubed, R to the 5, R to the 4 times R to the 3. That would be R to the 7, but R to the 6 is 1. So I get R. And then R cubed S, R to the 5S, and again, R to the cube times R to the 4 times S is just RS. And then you see that I did get all of these 6, so it satisfies that condition. What's the intersection of H and K? The intersection is just 1. There's nothing in common other than 1. And finally, is everything commuting? Now, notice that D6 is not abelian, so I can't say D6 is abelian, so therefore it works. So I have to check by hand that this is true. So first of all, let's take, if it's the identity commutes with everything. So let's see if there are two cases. In H, I could have the identity of R cubed. So how much is R cubed times, if I multiply by something in K that is just a power of R, then that is going to be 3 plus K, and that is R to the K times R3. So it commutes. So what happens if I multiply R cubed times one of the other elements, which are not just a power of R, the other ones are of the form R to the K times S. So is this equal to R to the K um, S times R cubed? Okay, so well, what I need to know is if I guess these are the powers of R that appear are even. So let me just write them as R2KS. I need to check if this is true. So what I need to know um, is this equal to that? Well, this is if and only if I can divide actually both sides on the left. I can multiply by R to the 2K and get that R cube as R cube, right? And here I can multiply on the left by R to the minus 2K to get that these two things are equivalent. And if I multiply on the right-hand side here by um, I'm going to multiply um, on the right by s, then I get r cube ss is s r cube s, which is in fact the same as r cubed equals s r cube s, because s times s is identity. And now recall that SRS is R inverse, and that implies that S R square S is R to the minus 2, and S R cube S is R to the minus 3. But in D6, R to the 6 is 1, so this is equal to R3. So this is true because of this, and therefore this is also true. Therefore, everything commutes. So hk equals kh for all k in k and for all h in h. So that is also satisfied, and therefore it is the internal direct product of the two groups. Now, what I've just proved is that D6 is isomorphic to that group H cross that group K, and H is just one R cube, is a group with two elements. It's a cyclic group with two elements, and we prove that every cyclic group with a prime number of elements is isomorphic to Z modulo P. So this is isomorphic to Z modulo 2. Now K, which is 1 R squared R to the 4 S R squared S R to the 4S. Now, what subgroup of D6 is this? Remember that D6 is the symmetries, the rigid symmetries of a hexagon. But if I restrict myself to this subgroup, instead of a rotation, there was a rotation, R itself sends this point to that point. That's what R does. So R squared sends this point to this point. So when you restrict yourself to only allowing the rotation to be R squared, what you're actually is doing the rigid motions of this figure instead. You see that now these sides are not well drawn. So let me draw it like this. So now what's happening is that these three vertices are the ones that we're doing rigid motions of those, because every vertex in this yellow is going to go to one of these vertices. So in fact, what happens is that what we are doing is the rigid motions of that triangle inside the hexagon, which is isomorphic to D3, and D3 itself is isomorphic to S3. So what we get at the end of the day is that D6 is isomorphic to H cross K, but H itself is isomorphic to Z modulo 2, and K itself is isomorphic to S3. And that is an isomorphism of D6 and Z modulo 2 cross S3, which is one of the isomorphisms that I talked at the beginning of this lecture. Great. Let me give you one last example, going back to our home of abelianness, so an example of an abelian group. Remember again that last time we showed that Z modulo 6 is isomorphic to the direct product of Z modulo 2 cross Z modulo 3. Then, well, that indicates that Z modulo 6 is a direct product. So it should be an internal direct product of two subgroups. So what subgroups are we talking about? I'm looking for a subgroup of order 2. There is, in fact, only one subgroup of order 2 in Z modulo 6. That's 0 and 3 modulo 6. That has order 2. K is the subgroup of order 3 inside Z modulo 6. There is only one, 0, 2, 4 modulo 6. And now you can see that H times K, the star now is addition. So how much is H plus K? All the possibilities are 0 to 4, or if I add 3, 3, 5, and 4, and 3, 7 is 1. So I get everything. So this is not just isomorphic, but exactly equal to Z modulo 6. H intersect K is just 0, and anything in H and anything in K commute because Z modulo 6 is abelian. So these three things tell me that yes, Z modulo 6 Z is actually internal direct product of that H and that K, and now that H is clearly isomorphic to Z modulo 2, and that K is isomorphic to Z modulo 3 because they are groups of order 2, cyclic of order 2, cyclic of order 3. So we get that isomorphism via an internal direct product as well. Okay, so that is it for external and internal direct products. And next time we will start with the topic of quotient groups. So we will first have to study normal subgroups and then do quotient groups.